Ready to go. Have a good session.
Thank you.
Thank you. Hello and welcome to session Machine Learning for Side Channel Attacks, where 6 papers will be presented. After each presentation, the speaker can take some of your questions, so please post those in the Zoom or here in the chat panel of Zoom. And yeah, if time permits, we can take more questions after we are done with all 6 papers. The first talk is given by, just a moment, it's going to be given by Gabriel Zaid and the paper entitled Ranking Loss, Maximizing the Success Rate in Deep Learning Side Channel Analysis. The paper was written by Gabriel, Lilian, Francois, Amaury, Alexander, and Gabriel. The floor is yours.
Thank you very much. Just before starting, can you clearly hear me and can you clearly see my slides?
Yes, we can.
Yes, we do.
Okay, thank you very much. So thank you very much for this introduction. So as mentioned, I'm Gabriel. I'm a PhD student from the Berkeley Laboratory and the TAIS ITSF. And the work I present to you today is a joint work with Lilian Bossuet and Amaury Abrard from the Berkeley Laboratory, and François Dassens and Alexandre Venelli from NXP Semiconductors. So the goal of our work consists in reducing the gap between machine learning metrics and the one used in side channel context, such that we develop a new ranking loss that aims at penalizing the learning process in order to maximize the attack success rate of a neural network. So when an adversary wants to conduct a deep learning-based side channel attacks, she first aims at developing a parametric function f theta, so that during the training process, the adversary wants to optimize the theta parameters in order to maximize the attack success rate for a given number of traces, so that the success rate metric can be expressed as follows. So here, the success rate defines the probability so that the score related to the secret key K-stars is higher than the score related to any other key hypothesis, so that in that case, the score is provided by the parametric function f theta. So during the training process, we want to penalize the neural network when this relation is not respected. But unfortunately, from an optimization perspective, optimizing the indicator function can be known as a difficult task. So first, we have to approximate it in order to penalize the neural network when this relation is not respected. So thanks to the work provided by Qin, Liu, and Li in 2010, we know that a good approximation of the indicator function can be made thanks to the sigmoid function, so that depending on an hyperparameter alpha, the adversary can monitor its approximation of the indicator function. So from this sigmoid function, we develop the ranking loss that penalize the learning process when this relation is not respected. So in other words, we want to penalize the learning process when the model probabilities provided by the model deviates from the true predictions. So such that the ranking loss can be expressed as follows. And one interesting point of the ranking loss that we demonstrate in our paper is that minimizing the ranking loss is beneficial to minimize the error provided on the success rate. Or in other words, minimizing the ranking loss is beneficial to increase the success rate for a given parametric function f theta and a number of traces. So, okay, once we develop the ranking loss function, we decide to evaluate its benefits from a practical perspective. And first, in order to evaluate its benefits, we have to introduce the following performance metric that we call NTGE, and that defines the number of attack traces that are needed in order to retrieve the secret key byte. So, and we denote NTGE bar, the average value of NTGE over 100 tests. Okay. And in order to assess the benefits of the ranking loss, we consider the ASCAD dataset that has been introduced to serve as a common database in deep learning-based side channel attacks. And the ASCAD dataset considers two countermeasures, namely the random delay effect with different level of desynchronization and the first-order Boolean masking. So to assess the benefit of the ranking loss, first, we develop a model that we train with the ranking loss function, and we decide to assess its benefits from a performance perspective with a model trained with another loss function that is called the cross-entropy loss function, and this loss function is widely used in deep learning-based side channel attacks. So to compare both models, we plot the evolution of the NTGE value following the number of profiling traces. So that the number of profiling traces are the number of traces that are used during the training process. And here in this plot, you can first observe the evolution of the NTGE value when the cross-entropy loss function is used, so here in green, and in blue you have the evolution of the NTGE value when the model is trained with the ranking loss. And once we conduct this experiment when no desynchronization occurs, we also evaluate the benefits of the ranking loss in comparison with the model trained with the cross-entropy when some desynchronization occurs. So first, through these figures, we can observe that for a given number of profiling traces, a model trained with the ranking loss performs, in the worst case, similarly to a model trained with the cross-entropy loss function. And on the other hand, for a given NTGE value, we observe that the number of profiling traces that are needed to reach this solution is lower when the ranking loss is considered. So from a practical perspective, considering the ranking loss instead of the cross-entropy loss function can be considered as a good alternative in side channel context. So if we want to conclude about this brief talk, first, by introducing the ranking loss function, we aim at reducing the gap between the machine learning metric and the one introduced in side channel context. And through our investigation, we observed that minimizing the ranking loss is equivalent to maximizing the success rate metric. Because, as I briefly mentioned, using the ranking loss is useful to penalize the learning process when the score related to the thick weight information, so to the private key K stars, is not considered to the highest value. Finally, if you want to get more information about the benefits of the ranking loss, we encourage you to read our paper because we provide some additional contribution. In particular, we investigate the impact of the ranking loss during the training process, and we perform a concrete theoretical analysis between the benefits and the limitations of the ranking loss in comparison with the cross-entropy loss function that is widely used in side channel context. And finally, we also provide additional experiments in order to assess the benefits and to validate the benefits of the ranking loss function from a practical perspective. So thank you very much for listening. If you have any question, do not hesitate to ask or to contact me over email. Thank you very much.
Thank you for the talk. There are no questions in Zulip yet, but I think Saba has a question to ask.
I have one question, and I think it was 2 slides before that when you showed the results for the ranking loss applied to ASCAD database. My understanding is that the framework made by you is quite generic, and you can use it for other databases. Have you tried that on ASCAD v2 to see what could come out?
Unfortunately not. We do not investigate the benefits of the ranking loss on the ASCAD v2, but we investigated on other data sets with a low level of SNR measures. and also on asymmetric implementations. And the results we obtain are always the same, and they are similar to those I introduced you on the ASCII V1 dataset.
Thank you. That was answering my question.
And there is a question from the chat. Ranking loss is considered a new metric to evaluate loss. Is ranking loss considered a new metric to evaluate loss? What's the advantage? Is it because less traces are needed?
So the ranking loss is not a new metric to evaluate losses. It is more like an alternative to the classical losses used in side channel context. Because if you want, thanks to a work provided at CHES 2019, we know that the metric classically used in deep learning approach does not totally reflect what an adversary wants in side channel context. So we have to adapt the classical learning metric used in deep learning approach in order to fit with what an adversary wants in our context. So what's the advantage in comparison with the cross entropy, for example? As we can observe through this slide, the number of profiling traces that are needed to reach a good solution can be considered as lesser. So lower. So if the adversary has to deal with a restricted number of traces, therefore it can consider the ranking loss function. But on the other hand, with the different experiments we provide on the ranking loss function, we also observe that in some cases we have some model that can retrieve the secret key using the ranking loss, while using other loss function don't.
Okay.
Hello?
Thank you.
Yeah.
Oh, sorry.
No problem.
Thanks. I think we need to go to the next talk now. If you have more questions, you can post in Zulip. So the next talk is titled Keep It Unsupervised Horizontal Attacks Meet Deep Learning. And the authors are Galimer Perrin, Lukasz Hamielowski, Leila Batina, and Stefan Piczek. Galimer, the floor is yours.
Yeah, thank you very much. Are you seeing my screen? Can you confirm everything is okay? Okay, good, thank you. Hello everyone, thank you for joining this session. So I will shortly present a summary of our paper, Keep It Unsupervised, Horizontal Attacks Meet Deep Learning. So what we propose is a framework to improve horizontal attack results using deep neural networks. So horizontal attacks in practice, just very briefly to introduce the context, it's a very limited attack in some cases because it can show very low accuracy. So, and then in our case, we use unsupervised clustering attacks using k-means technique to retrieve the key. And we did a very simple initial attack where we recovered 52.2% of the key. And what our target device, as I will show later, is a ECC implementation software. So the basics behind our idea is that deep learning can be efficient in some cases when you have noisy or wrong labels. And then for that, as you can see in this illustration, let's say the dashed labels here are the ones that will be wrong. And then in our case, we have two classes, the key bits 1 and 0. And when you train a regularized network using these noisy labels, and you predict with a separate validation set that also contains noisy labels, the network can, if the regularization is working well, it can predict the labels correctly or with less wrong bits, wrong labels at least. And so we propose the framework here. We propose the framework that can iteratively recover let's say, correct the wrong bits during the process. And the process is the following. So firstly, we take the full data set that contains all the subtraces that are cut pieces from the full traces in a horizontal attack way. And the traces are initially labeled with a horizontal attack. And then we train in the second step, we train 2 separate models, which each subset that are part of the first, the big subset, the big training set. And then in the next phase, what we do is to swap data sets. And then we predict the network that was trained with one subset with another subset. And then the prediction now, because the network is regularized and able to deal to correct the part of this wrong labels, it will predict with a lower error rate in comparison to the first case. So, and then at the end, the final we combine the traces into one group again, and then we shuffle them and then restart the process again. And then in our work, we did this process by iteratively by 50 times. So we tested different scenarios also, where the networks during the iterations are can be fixed. I mean, the hyperparameters can be fixed or can be randomized during the process. So for each iteration of the framework, we can also select a random group of hyperparameters. And then we tested different regularization techniques that are very common for deep learning domains, especially in sidechain analysis, that is dropout and data augmentation. So we consider 2 different data sets for our case, which is the first data set is, so the data set comes from the same device, which is a software implementation on ARM Cortex-M of ECC, of scalar multiplication, of curve 25519, which is a Montgomery ladder implementation of scalar multiplication. And then the main difference between the 2 data sets is that in the conditional swap operation for constant time. And one is computed using arithmetic means, and the other is using pointer swapping. So we measure 300 traces, 300 scalar multiplication. Every scalar multiplication has a random it has a random private key, which is a random scalar. And then we split all these traces into subtraces, which will give us, 76,500 subtraces. And we use 250 traces for training and 50 traces for testing. So here, just to summarize some of the results, you can see that during the iterations of the framework iterations, we can, when we start with a very low accuracy, around 52%, during the framework iterations, we gradually increase this accuracy of a single trace. Let's say this single trace accuracy means the best accuracy out of 50 scalar multiplication traces. And sorry, I don't know why my slides are going to the next. Then we can see that for situations when we have regularization, especially in the second data set on the right, it converts very fast to 100%. And for this SysSwap arith data set, it's a bit more difficult data set, and then it takes more time, but also we can see that combining multiple regularization methods, which is dropout and data augmentation, it goes to 100% as well after something like 54 iterations. But when you use data augmentation only on this data set or no regularization, you can see that the attack doesn't work. Even if in the SysSwap pointer data set, which is easier than the first, it doesn't reach 100%. When we also randomize the hyperparameters during the framework iterations, you can see that for the first data set, the results are slightly better. But for the second one, the result doesn't improve. So testing with different cases, you can see that the results can get a bit better when you use a different combination of random hyperparameters. We also improve the bit results for some cases when we use gradient visualization to trim interval. In this case, we can select a sub area of the trace in order to focus on where the leakage is happening. And then we observe that the gradients are higher when the leakage is located on the trace. So if you compare the signal to noise ratio to the gradient, you can see that the peaks are located more or less around the same places. So just a final slide here to summarize what we got. We tested many different scenarios. So for each scenario, we ran the algorithm, the framework 10 times. And you can see that in some cases, we don't succeed at all. Like say when we have no regularization, for example. But when we add some regularization to the scenarios, we can sometimes succeed, sometimes we don't. But what we see is that the results are largely improved when you have when you consider gradient visualization, especially for C-swap arith dataset. And when we, in the first case, we succeed 1 time out of 40, and when we trim the interval, we succeeded 19 times out of 40. So using the deep learning mechanisms to improve the attack, we can drastically, significantly improve the attack results. For the other data sets, the gradient visualization doesn't improve so much, but using regularization, of course, it's the key element to make successful. So just a summary and conclusions of the work. So in this paper, we show that we propose that a new supervised attack combining horizontal attack and deep learning approaches that can iteratively improve and correct the wrong bits in the private key obtained from the horizontal attack. And we observed that regularized neural networks are the key to do this. And we assume that this framework should be applicable to other public key implementations, for example, RSA, modular exponentiation, for example. And we plan to investigate for now some other benefits from the framework, for example, against trace misalignment, or analyzing how the label initialization process from the horizontal attack can interfere in the attack results, for example. Yeah, so this is my short presentation. I'd like to thank you. And if you would like to check out our code, is available in this link. Thank you.
Thank you for the interesting talk. There is one question asked in the Zulip that reads, in your experiments, you started with a very low accuracy, let's say 52%. Maybe hope to correct errors with your methodology starting by a lucky totally random clustering? I guess no, that was the answer of this attendee. Thus, my question is, what kind of information must be brought by the initial clustering?
If I understood correctly the question, so this is about how to initialize the labels,
Exactly.
how to make the initial labels properly for the framework to work. So we tested already some random labels initially to see how it worked, because the 52% is very close to random, if you see. And then, but it's if you look at the paper, some of the figures, we do a leakage assessment on this 52%, and then you can see that even if with 52% of accuracy, you can still more or less signal to noise ratio peaks around the same real leakage parts. But of course, in many scenarios, as I try to show in this slide here, we don't succeed. So the higher the initial accuracy, of course, the better. But in many situations, if you are very close to 50%, you will not succeed. But if you go slightly above, there are chances that the framework will start correcting the bits along the framework iterations. So we can be, we believe we can be still lower than 52, the initial level. Yeah, I don't know if I answered the question, but that's why I understood it would be the way.
Thank you. I suggest that if there is any follow-up question, you can ask after this session or just via Zulip. And if you agree, we can go to the next talk, because I don't want to run late. The next talk will be given by Xiangjun. Let me first thank Jan for the nice presentation. I just forgot about it. It's late in the USA. Sorry about. So the next talk will be given by Xiangjun, and the paper is entitled "Pay Attention to Road Traces: A Deep Learning Architecture for End-to-End Profiling Attack." And the paper is written by Xiangjun. She, I think it is pronounced Pei and Down and Henning. Xiangjun, the floor is yours.
Okay, thank you. Can you hear me and see my slide?
Yes, we can.
Okay, thank you. Okay, let me just okay, hello everybody, welcome to this presentation, and I will be giving a talk about our recent chat paper, Pay Attention to Road Traces, Deep Learning Architecture for End-to-End Profiling Attack. So let's start with the basic motivation of this work. Deep learning has been widely used in the set channel analysis in recent years. Many works have defeated the countermeasures and addressed the desynchronization issue simultaneously by deep learning. However, in almost all of these papers, the selected narrow trace intervals instead of the row traces are used, even when the implementation is protected by masking. That means there is a manual feature extraction before the profiling. But if we consider a practical black box analysis on a master implementation, locating the leakages is arguably the most challenging part of the whole analysis. Therefore, we argue that to fully utilize the potential of deep learning and get rid of any manual intervention, we need the end-to-end profiling that directly maps raw traces to target intermediate values. So in our paper, we propose an end-to-end architecture composed of encoders, attention mechanisms, and a classifier to conduct the end-to-end profiling. And here is our new architecture. We propose this architecture to profile raw traces no matter they are desynchronized or protected by masking. As we can see in this figure, the encoders will first encode raw traces to the abstract features. Then the attention mechanism will give each feature a score and weighted sum them up. Finally, the classifier will generate the probabilities from the final feature vector. Next, I will give a brief introduction of each component in our architecture. First is the encoder component. The encoder component includes two parts, the junior encoder and the senior encoder. In junior encoder, we use the locally connected layer or stacked convolutional layers to encode the raw traces and get the fine-grained features. For the senior encoder, we use the long short-term memory. We use LSTM because it could learn to control the data flow automatically when it goes through the sequential data. And there are 3 gates in LSTM, and these gates will control what information is collected, forgot, and yielded. And there are also other great properties of LSTM to handle the long sequential data. The LSTM in our architecture works under the sequence-to-sequence mode because encoding a too long sequence into a single feature vector is still too hard, even we use the LSTM. So we need the attention mechanism to reduce the hardness, and exposing the hiding state of LSTM is just the precondition to use attention. And the next is the attention component. The attention mechanism evaluates each feature vector H generated from the senior encoder and give each of them a probability. So it essentially parts the sequence by the probabilities where the value is large enough. So the LSTM could focus on the parted subsequences rather than the whole sequence. And for implementation details, we modify the bottom-out attention and use the variant with an additional batch normalization for better performance on the raw traces. So what do we get through our new architecture? And here is some basic information about our experiments. Basically, we use the identity label and we consider both synchronized and desynchronized scenarios. Below are the data sets we used, and you can see in the fourth column that we could use over 400,000 time samples directly.
To save time, we only show the attacking result of ATCAD dataset. We refer to our paper for more detail. We can see in the third column that for the synchronized traces, we need only 6 to 8 traces to recover the case of both ATCAD V1 and V2. For the desynchronized scenario, we find that the number of traces is not quite enough, so we conduct data augmentation in this scenario. And as a result, we could also reduce the get entropy to 0 with very few traces. And here is a summary of our attacks on different data sets. The second column is the random delay we used to simulate the desynchronization. And the third column is the number of traces to recover the correct key. You can see that for most of the cases, we could reduce the get entropy to 0 in several traces. Therefore, our attacks are even more efficient than the networks trained on the shortened traces. And finally, I will show some visualizations of our network to explain how the attention mechanism works. The visualizations give an insight of how our attention mechanism focuses on the informative interval. As we can see in the subfigure F, we plot the probabilities of forward and backward attention. We could observe that both attention instances pay special attention just after the LSTM goes through the time steps between about 800 and 900. And these time steps correspond to an interval around index 45,000 on the raw traces. In other words, this interval is suggested by our attention mechanism to be the most informative interval on the raw traces. And not surprisingly, this interval includes the 700 time samples that are manually selected by the authors of ATCAD. So our attention mechanism could indeed find out the informative interval. Okay, finally, we move to the conclusion. In this paper, we introduce a neural network architecture for end-to-end profiling. That means rather than leveraging the knowledge of implementations to manually locate the informative intervals, we could profile the raw traces directly now. We also introduced some new structures into the SAE field to build the architecture, like the locally connected layers and the attention mechanism. Besides the effectiveness, we find our approach working under the end-to-end context performed even better than the networks trained on the reduced traces. And we also explore how the attention mechanism works in the set channel context to verify that our architecture works as we designed. So this is the end of my short presentation. Thank you for listening, and I'm willing to answer all of your questions.
Thanks for your presentation. There is a question. Did you label the traces with just, for example, first round intermediate values, but trained using full round, that is 10 round traces?
Yes, we just label the traces with the output of S-bots in the first round, and in training we could use all the full-length raw traces.
Oh, thanks. Next question is how long does the training phase for end-to-end profiling model last? Have you ever encountered convergence issues, which is often met with deep learning-based set channel analysis, especially against mask implementations?
Yes, we give some statistics in our paper about how long it will take to converge end-to-end profiling. So generally, it will take more than 1 or 2 days, but most time it will converge in several days. Okay. Okay, that's it.
Okay, thanks. We need to move to the next talk now, and if you have more questions, you can post in Zulip. So the next talk is titled DLLA, Deep Learning Leakage Assessment, a modern road sorry. A modern roadmap for SCA evaluations. The authors are Sorben Moos, Felix Wegener, and Amir Moradi. Sorben, the floor is yours.
Okay, thank you. Thank you for the nice introduction, and also thanks for joining to this short presentation of our paper. This work deals with leakage assessment, and leakage assessment is essentially a technique we use to determine whether input-dependent information is included in side channel measurements of a device under test. The most common approach to do this is trying to distinguish leakage distributions for different input classes using a statistical hypothesis test. And the most commonly used input classes for that are fixed versus random and fixed versus fixed. And the most common statistical hypothesis tests are the Welsh t-test and the Pearson's chi-square test. These classical tests have been used for many years in the side channel community, and they are a great tool for many purposes. However, they also have some drawbacks. And the main one is that the tests are normally applied to each point in the trace individually and independently. Therefore, they are typically not able to detect leakages which are spread over multiple time samples, like multivariate or horizontal leakages. And also the separation of statistical orders in the t-test has been shown to lead to false negatives in some corner cases. So we thought about different strategies and have noticed that leakage assessment is essentially a statistical classification problem. If we are able to build a software that determines correctly whether a given side channel trace belongs to group 0 or group 1 with a better success rate than guessing over the whole set of traces, then we can conclude that input-dependent information is included in the trace set. And to us, this sounded like a perfect application for deep neural networks. So how is this done? First, we record a set of side channel measurements in fixed versus fixed manner. Then we split the whole set into a training set and a validation set and train the neural network on the training set. Afterwards, we use a trained network to classify the traces in the validation set while hiding the true labels from the network. Then we determine the number of correct classifications achieved by the network on the validation set. And what we are able to do with this number is calculating the probability that this amount of correct classifications could have been achieved just by chance by a classifier that is merely guessing. And if this probability is below a certain threshold, we reject the null hypothesis because we can conclude that indeed information is included in the traces, which allows classification into the two groups. And in fact, the trained classifier does not even need to be very good at classifying in the sense that it achieves a very high validation accuracy. It only needs to classify slightly more than 50% of the traces correctly if done over a large enough number of traces. For example, of a total of 182,200 traces, the classifier only needs to get 50.5% correct to confidently reject the null hypothesis. Here is one case study based on a presence threshold implementation measured on a Spartan 6 FPGA. We can clearly see that the third order t-test and the chi-square test detect leakage. The largest amplitudes reach slightly above 20 and slightly above 50 in terms of minus log 10 probabilities after 10 million traces. When training our deep neural network on 3 million traces over 50 epochs and validating on 1.5 million traces, we get confidence values above 1000, again in terms of minus log 10 probabilities after 50 epochs. We can also see that the sensitivity analysis or the gradient visualization on the left side shows that only the most leaky part in the middle of the trace is really used for the classification. The other parts of the trace are apparently ignored because likely they carry only redundant information for the classification. The next case study is also based on a presence threshold implementation, but this time its shares and component functions are clocked sequentially so that the circuit exhibits no univariate but only multivariate higher order leakage. We can see here that the univariate tests The third order t-test and the chi-square test do not detect any leakage with up to 50 million traces. However, a multivariate extension of the third order t-test using the correct offsets can detect it after roughly 45 million traces. For a real-world scenario, if the underlying source code is not known, this requires intense reverse engineering and expert knowledge, because the exhaustive methods for this kind of evaluation are mostly too complex to be really carried out. In my personal experience, even when knowing the underlying implementation, this is not always super straightforward and always requires some manual work. The deep neural networks, on the other hand, do all that work for you automatically. Here we have trained it on 20 million traces and validate its classification ability on further 5 million traces. And we can see that after 25 epochs, the detection threshold is overcome and a pretty high confidence is reached after 50 epochs. Okay, in summary, leakage assessment using neural networks is indeed feasible and also worth the extra runtime in more complex detection scenarios, as for example, multivariate higher order leakage, since the deep neural networks are able to learn many forms of leakage automatically without any pre-processing or manual effort. Also, the analysis often requires fewer traces than classical tests because the detection is based on the full trace at once and not on each point or a combination of a few points individually. The confidence produced is also orders of magnitude higher usually, and the risk of false positives is reduced when the same threshold is considered because you only give one value instead of one value per point of the trace. Okay, that's already all from my side, and I'm happy to take any questions.
Thank you, Torben. That was really interesting. There is one question that reads, is there any particular reason you opted for fixed versus fixed instead of fixed versus random, which might be more common?
Yes, indeed, because even in simple cases, you have with fixed versus random, a larger overlap between your distributions at each point. With fixed versus fixed, you can get like completely distinct distributions with fixed versus random because the fixed distribution, so the fixed is also part of the random group, so there will always be a larger overlap. So for better distinction, fixed versus fixed is really the better choice here.
Question in the Zulip, and let's call it the last question in this talk. Can you hear me? Because I think my internet is not very stable, the connection is poor. The question is, can you also use the network you have used to identify leakages to perform key recovery attack?
Yes, so we have not done this in this paper, but essentially you can do exactly that. So first you can, of course, find the location of any leakage, like a typical leakage assessment, but you can also identify specific leakages for an S-box output bit, where you also have two classes and you can perform completely the same strategy.
Thank you. There are other questions in the Zulip. I would like to ask Torben to go through them offline. Thank you.
Okay.
So the next talk will be given by Li Chao, and the paper is entitled Reinforcement Learning for Hyperparameter Tuning in Deep Learning-Based Side Channel Analysis. The paper is written by the paper is written by Yuri, Li Chao, Guillaume, and Stepan. Li Chao, the floor is yours. We cannot hear you. You are muted. Can you please unmute?
Yes.
Yeah, that's perfect.
So you can hear my voice and also see my slides.
Yes, we can.
Yes, thanks for the nice introductions. And my name is Li Chao Wu. And today I'm gonna introduce our recent work, Reinforcement Learning for Hyperparameter Tuning in Deep Learning-Based Side Channel Analysis. And this is a joint work with Yuri Reistak, Guillaume Perrin, and Stefan Pisak. So So profiling side channel attack is part of the side channel attack, and it's really powerful because it's under really strong assumptions. Assume that the attacker have the full control of the clone device. So to perform a profiling side channel attack, there are two phases. The first phase is doing the profiling, so building the profiling models with profiling traces and labels, and then just use the attack traces acquired from the attack device and ask the profiling model to do the prediction of the attack labels. There are two popular profiling side channel attack, template attack and deep learning attack. Recent work shows that the deep learning attack is really powerful, especially in dealing with the traces with countermeasures. However, develop such a network is not that easy, especially there are so many different hyperparameters, such as network types, layer configurations, and training configurations. And it's not that straightforward to design such a network, and that can be easily applied to different data sets. So the goal of this work is to automate and to simplify this process and help the evaluator and attacker to develop a better network that is suitable for the dataset. So we are using reinforcement learning, more specifically the Q-learning. So this is the plot to illustrate how the Q-learning works. So basically, this is just an interaction between the agent and the environment. So the agent is knowing better about the environment based on the objective we set to them. And for the side channel context, the objective will be founding a good network. And the following equations also represent this diagram or this plot. So it's based on the Bellman equations. And besides the details, which you can find in the paper, this calculate the Q value, which is a quality value of the current state action pair. The state is the state of the agent, and action is the agent takes actions based on the current state. So calculate this Q value is important because it gives us reward on the current state action pair. And as you can see in this equation, besides the other factors, the reward is really important because as I said before, the reward sets the object to the objective to the agent. And we want to let the agent to explore the environment, which is possible network topologies and gives us a really good network that's suitable for the specific data set. So we design the reward with the different evaluation matrix, especially side channel evaluation matrix. So basically there are 4, and there are additional one, I will cover it. So we consider the percentage of the traces that requires to convert to gas entropy 0. And also we evaluate different gas entropy value with different number of the traces. And also we notice that there are papers focused on finding a good performed network, while the network should be small because it's easy to be trained. So we also consider the trainable parameters, which is a p-value. So from this, we developed 2 different versions of the reward function, which is reward and reward small. And reward small stands for the reward function that we want to find the small but good attack models or deep learning models. So this is our network searching method. So we start by sample the network topologies, then we train the network, and finally we evaluate and update the Q values. And we repeat this process again and again with epsilon graded schedule. So the details can be found in the paper, but the goal of this schedule is just to balance the exploration and exploitations. And also for some details, the sample of the network topology is followed by some rules, and the rule is defined by the latest state-of-art research. And for the details, please find it in our paper. And by the way, there are batch normalization and gap layer, which is not really commonly used in recent papers, but we also consider it because it is possible to produce models. And finally, we move to experimental result. We have experienced 3 data sets, but here we only show 1 ASCAT-FIXI data set, which is ASCAT version 1. So here's the result. From the left, you can see our searching overview. So for each dot, it stands for the one network topology. And the x-axis stands for the Q-learning reward, which is the reward I just mentioned before. And the y-axis stands for the number of the trainable parameters. And the cross of 2 red lines stand for the state-of-art models. So we want to benchmark with the state-of-art models. So as you can see that we have tested different leakage models and different reward functions. And apparently the models on the right down corners performs better than the state of art because it reaches higher Q-learning reward with smaller trainable parameters. So in both cases, we can find good models. And here's the benchmark. On the right the table, you can see the benchmark. So for both reward functions, we can get really small models, but the performance is really good or even better than the state of art. And also we show the reward during the evaluations. And as I said before, we use epsilon graded schedules. And when we're moving from the exploration to exploitations, you can see that the reward is actually going higher. This means that our agent is learning better about the environment. And also we test our base entropy and it performs really well. So finally, we move to the conclusion and future work. So in this paper, we propose a reinforcement learning framework that enables automate and powerful search for convolutional neural network for profiling side channel. We motivate and customize our reward functions, and we demonstrate the effectiveness of our method. And for the future work, it will be interesting to investigate the deep Q learning paradigm, and also how is the best models works with ensembles of the models. And also we want to apply our searching methodologies for other type of network. Thanks for your attention. And if you are interested in our code, please check this link and you can implement our schemes really easily. Thank you.
Thank you for the presentation. There is a question. Interestingly, finding good hyperparameters while penalizing bigger architectures has somehow been addressed with, for example, structural risk minimization or minimum description length. Both approaches theoretically explain how to properly set a penalizing term for bigger architectures in hyperparameter tuning. Have you compared your algorithm with any of those approaches? And if so, which works the best?
Thanks for the question. Actually, it's a really good one. So the initial thought of our initial design of our reward function do not consider the trainable parameters, because we believe that for the side channel network, it's already super small compared to the traditional deep learning models, but still we added. But unfortunately, in this paper, we do not compare it with other searching methodologies that can penalize the bigger network. But we believe that we can also easily apply in our scheme by designing a new reward function that emphasizes that we need to find a smaller but good performed models.
Thank you. Due to time constraint, we will move to the next talk now. The title of the next presentation is Cross-Device Profiled Side Channel Attack with Unsupervised Domain Adaptation. And the authors are Cao Pei, Zhang Chi, Lu Xiangjun, and Gu Dawu. Cao Pei, the floor is yours.
Yes, can you hear me?
Yes, yes.
Okay, thanks for the introduction. Hello and welcome to our paper Cross-Device Profiled Side Channel Attack with Unsupervised Domain Adaptation. So in this work, we focus on the open question of portability, which is a major limitation of profiled attacks. The portability issue occurs when there is a gap between experiment settings and reality. For example, in experiments, we usually use a single device for profiling, and then we use the same device for the attack. But in reality, the profiling device and the attack device are different in most cases. Even for devices of the same type, the leakage of the side channel information is inevitably different. Unfortunately, this device discrepancy information is not utilized in these classic two-phases profiled attacks. As a result, attacking a different device may cause a successful single device attack to fail. Today, device discrepancy is still a bottleneck restricting the application of profiled attacks in practice. So in order to address the portability issue, we propose to extend the traditional profile attacks and introduce an additional fine-tuning phase to adjust the pre-trained model. Fine-tuning is a widely used technique in transfer learning for deep neural networks, where a few approaches of training are applied to the pre-trained model's parameters to adapt them to a new task. A straightforward approach for fine-tuning is to take a pre-trained model and then train parts of its parameters using the data from the target domain. However, in realistic profile tags, there is no labeled trace measured from the target device. So in our strategy, the inputs of the fine-tuning phase are the original profiling traces with known labels and a limited number of unlabeled traces measured from the target device. Our network should capture the discrepancy information of the two domains and to learn domain environment features. So in order to capture the discrepancy information, we must decide how to quantify the distance between the profiling and attack traces. So in this work, we introduce the maximum mean discrepancy, which is a standard distribution distance metric and has been widely used in many other transfer learning tasks. So in order to learn domain environment features, we must design new loss function. The loss function is composed of two parts, a classification loss and a MMD loss. The classification loss makes sure that the learned features are discriminative. In our experiments, we use cross-entropy loss by default. The MMD loss tries to make the two domains appear as similar as possible. It can be regarded as a constraint term with a penalty parameter lambda. As for the architecture, there are two main differences between classic CNN models and our architecture. First, our fine-tuning network receives two batches of traces for each training process. Specifically, one batch of labeled traces is acquired from the profiling device. The other batch of traces is unlabeled, acquired from the target device. The second difference is we have to decide where to calculate the MMD loss in our network. Actually, previous works have shown that deep features must transform from generic to task-specific as one goes up the layers of a deep CNN. Therefore, we decided to minimize the MMD loss on the fully connected layers. The convolutional blocks of the network is still trainable during the fine-tuning because we expect them to learn shift environment features in case the target domain is not well aligned. The figure on the left shows the 8 X-Manga chips. We initialize each device with a different secret key. We can see from the signal noise ratio that the leakage differs. For example, the device 4 is shifted apparently in time. These are the results on the X-Manga dataset. We can compare the performance of the pre-trained models and the fine-tuned models. The results of NT donates the number of attack traces to successfully recover the key. For pre-trained models, we can observe that although the value of NT for single device attack given on the diagonal is very small, it varies widely in the case of cross-device attacks. In fact, the better performance of cross-device attacks can also be explained by overfitting. We therefore draw the learning curves when we train the network. The red curve is the test loss on the target device. It's interesting that the test loss increases rapidly when we train the network, which means the model is already overfitted in the first fail approach. Unfortunately, this kind of overfitting is hard to identify because in realistic attacks, the attack traces are unlabeled and cannot be used to calculate the test loss. After fine-tuning, the performance of cross-device attack is very much improved. We also draw the learning curves when we fine-tune the network. The curve in blue is the MMD loss that we add to the loss function. The curve in red is the test loss on the target device. We can see that minimizing the MMD loss can effectively reduce the test loss on the target device. So what's the cost of this approach? In our experiments, we can observe that the approach time for fine-tuning is about twice that of training. However, the time cost is still affordable. For example, if we during the fine-tuning phase for 15 approaches, this process can be completed within 2 minutes for all these datasets. So finally, we move to the conclusions. This work focuses on the open question of portability in profiled set-channel attacks using transfer learning techniques. Although CNN is known to be robust against misalignment, we show that CNN may not generalize well if only clean traces are fed. However, after fine-tuning with MMD loss, our network is able to learn domain environment features. Besides, this approach does not require multiple profiling devices. target-specific preprocessing and information of the target device. So thank you for your attention. And if you have any questions, feel free to ask. Thank you.
Thank you for the nice presentation. I cannot see any questions asked here in the chat panel or via Zulip. If there is no question, I can ask one. When you say that CNN may not generalize well if only the clean traces are provided, I think I missed that point where the not clean traces were used. Do you use them for the training, and the noise in that traces are used to do regularization, or actually I'm not sure how you use those not clean traces?
Yes. In fact, in our paper, we also test our approach on the desynchronized data sets. For example, the ASCD, we add a random misalignment to the row traces, and we use our approach to remove the misalignment, the effect of misalignment, and yes, it works.
I see. Thank you. Definitely, I will take a look at your paper again because that's very interesting. There's no other questions, and there was one question remaining in the chat panel. I copied that in the Zulip. I asked the attendees just to check again the Zulip for the answer to that question.
Thank you.
Okay. We would like to thank the speakers and attendees of this session, and